So now let us record some examples where we show the spaces are not homotopically equivalent. So the first example is CP2 is not homotopically equivalent to S2 wedged with S4. So first notice that both these groups have the same homology and cohomology groups. So in fact it is important that the cup product will be used to distinguish between these two spaces. So obviously we have graded rings associated with these two spaces, but within those graded rings the cup product acts very differently. Now we have seen for the graded ring of H star CP2 already that the multiplication is non-trivial. So you have alpha in CP1 and you can take alpha cup alpha and it will be non-trivial. But here in the second part, S2 wedged with S4, the cup product is trivial. So let us show that. So the generators lie in H2S2, which is the non-trivial group. So this alpha, say alpha 2, lies in H2, the second part, because that is the non-trivial part, and similarly for the fourth part, H4. So H4 S4 it should be. I will just correct it. So alpha 4 lies in H4 S4, but alpha 2 cup with alpha 4 is 0. Now this is not so that the cup product is trivial. This is trivial precisely because of the wedge products. Because of the wedge products, the graded rings will split in a particular way and therefore the cup product will be trivial. So here you can see alpha cup alpha in H star CP2 is not 0. So you can see that the graded ring structure is very different and therefore CP2 is not homotopically equivalent to the wedge product of S2 and S4. Now we want to show RP3 is not equivalent to or not homotopically equivalent to this RP2 wedged with S2. So first note that in integers both have this trivial cup product. So you have trivial one-dimensional cohomology groups, and therefore you can't say much about the graded rings. So you just have trivial one-dimensional cohomology groups and therefore nothing can be said. So the case becomes more interesting in Z2. So we have to go from integers to Z2 to say anything about this. So in RP3 we have say alpha belongs to the first group. So then we know that alpha cup alpha lies in H3 and this is non-trivial. So we have already talked about the graded ring structure of RPN. But for the case of RP2 wedged with S2, we have a completely different structure. We have say alpha 1 which belongs to the cohomology part H1. So alpha 1 cup alpha 1 is non-zero and it lies in H2. Whereas beta lies in H2S2 integers. So notice that alpha 1 cup alpha 1 is not equal to beta because of the wedge product. Because of the wedge product, the graded ring kind of splits as a direct sum. So the ring structures are completely different here, and therefore Rp3 is not homotopically equivalent to Rp2 wedged with S2. So the third important example is Sm times Sn is not homotopically equivalent to this part. Yeah, so first notice that both these spaces have identical homology and cohomology groups. So it is only with the help of the ring structure that we are able to determine that these two spaces which have identical homology and cohomology group are different, are not homotopically equivalent. Again, you have to keep this thing important in mind. How does the graded ring act on the wedge product? Now, we have mentioned this before in the previous application of graded rings, that when you have wedge product H star x wedge with y, it splits it splits as a direct sum H star x direct sum H star y, and therefore in wedge sum generally the cup product is trivial. So you have two elements in two different wedges. When you take them together, they will not land in the third wedge. So you have these three non-trivial generators. Obviously, we have alpha 1 corresponding to Hn Sm times Sn, alpha 2 corresponding to Hm, and alpha 1 cup alpha 2 lies in Hn plus n. So notice that this is non-trivial. So for the wedge product, you see that there are three elements: beta 1 which lies in HMSM, yeah, so say the nth part, then we have beta 2 which lies in M part, and then we will have beta 3 lying in M plus N part. Now the cup product here in this case is trivial. Yeah, because it's a wedge product, you do not land at the higher group.